Welcome to this talk on co-piloting autonomy. With me are Heidi and Ankita from Cobot. And to kick things off, Heidi, perhaps you can give us a quick introduction to what Cobot does and all you know about proxy.
Sure, yes. So Cobot's vision is to build robots that work alongside people and really at scale. And the focus is in situations where you don't build a lot of infrastructure with the robot, you just bring the robot in. So our customers are in logistics, manufacturing, and in healthcare. First robot is Proxy, and Proxy is designed for materials handling. In designing Proxy, we wanted a robot that was trustworthy, useful, and adaptable. And so trustworthy, we really looked at that both in the aesthetics and the design of the robot, so it looks like it's something you could trust and you can look at it and see what it does. And then also when we're designing the motions and the performance of the robot, we want it to behave in a trustworthy way. Useful, we've started out with a bot that moves carts around, and it moves carts that today are moved by humans, so it can adapt to lots of different kinds of cart sizes and handles and types. And then we also designed Proxy to be adaptable. So today it adapts to different carts. We can swap off the arms that today are designed for cart pulling and get arms that are maybe by manual manipulators or other arms that could manipulate other things in the environment.
Nice, yeah, I love the trustworthy design. It has these big friendly eyes.
Yes.
It's a very, very nice design. And yourself, Ankita?
Yeah, so I work on safety. So even our safety approach at Collaborative Robotics is very much rooted in this idea of trustworthiness, as Heidi mentioned, because we deploy robots in a lot of different settings. Like, as you can imagine, your warehouse setting is drastically different than what a hospital setting is like, but we have one platform that must navigate both of those environments, right? So yeah, we really take a holistic approach for safety as we go about that.
So you keep mentioning the word safety. If you're doing indoor mobile robotics, what does that actually mean in practice? Can you give us a little bit more detail?
Yeah, so I think, I know there are a lot of great roboticists in the audience here, and also earlier today we heard a lot of different glimpses of the safety conversation. But let's take a few step backs, because the story of safety really starts from deployment, right? Like, where is your machine going to be deployed? And what is your machine going to do in that space? And so with this layer of deployment and where the robot's going to go, there's a lot of different things that get baked into this umbrella term of what safety is, right? So especially as you see robots now being more a part of your personal and private space, like hospitals or medical centers, definitely security and privacy gets baked into safety. But as Heidi spoke about earlier, there's definitely this idea of trust, which is, does the robot look and behave in a trustworthy manner? And that means not just the human and robot interaction, but also the fact that even the robot by itself doing its motions and doing what it needs to do, a bystander looking at it it will seem that the robot is doing the intuitive thing, right, for the bystander. So there's definitely those aspects, and from a safety perspective, I loop all of that into this term that I like to call inherent safety by design, which is you want the robot to do the right thing. But then there's the other side of the coin, which is, given what the robot is supposed to do, or what it does, it should do that at a level of consistency and repeatability. And that's where the term reliability, or reliability for a safety target, comes into play. So kind of going back to your deployment, right? Because hospitals and warehouses and industrial settings are so different. And we also know that you can't never 100% get rid of risk. The question really becomes, what is then your acceptable level of risk? And all of these different deployment sites have a very different risk appetite. So it's just inherently safe by design is not sufficient. That's where you do have to go back to more of your traditional functional safety and traditional risk assessment formal methods to really quantify that risk, so that you as a deployment engineer or roboticist in a company feel confident in the way that you're approaching safety, right? So yeah, I think safety in practice is very much that trustworthiness coupled with reliability also.
No, that's awesome. That's awesome. Yeah, I can imagine, in these different areas, you do have different targets, as you said, how safe you have to make it for different scenarios. And you talk a little bit about inherent safety, and a brick on the ground is inherently safe. Nobody picks it up, it's fine.
Yeah.
Right? But there's another side to the coin, which is you actually have to get the medicine to the person, or you have to deliver the tote to the facility. So, for you, Heidi, how do you avoid this kind of tug of war between safety and productivity, and how do you actually co-pilot these teams? I'm sure trust is part of that, but what does that actually look like?
Yeah, I think that this is a good question, because you can get in a place where you feel like, the safety team will handle the safety, the autonomy team will handle the autonomy, and that's never how we want to do it. We want to do it that we're on the same page trying to do the same thing. So I think one way to think about it is, what is it that you want your robot to do? And so for Cobot, I mentioned trustworthiness as being key, and I think that's really key for any of these robots that we're building, because if they're going to be around people, we need to trust them. And then the other side of the coin is performance. We want them to do a task, we want them to do it well, we want them to do it reliably. So if you start with, okay, we've got these trustworthiness and performance goals, well, they're really then the same goals for autonomy and safety. So both autonomy and safety want them to be reliable, want them to be performant. And the autonomy side is going to think about, okay, how do I meet those performance goals? So you design the system to meet your trustworthiness goals, your performance goals, and you think, okay, from the autonomy side, I want my sensor to predict far enough ahead so that I can perform well. And then the safety side will say, well, I need that sensor or a different sensor that can look enough ahead to see if there's a safety risk, and then I need the robot to stop. So you really design this together and do your system design so that it's going to meet both your autonomy and your safety requirements.
Yeah, that makes sense. So, Ankita, a question for you. If Heidi's done her job, she's designed autonomy, it's working great, what is the actual biggest safety challenges that you face when you're trying to take that system and make sure that it's performant?
I think kind of going back to what we were saying, right? Like when you take a robot from one site to another, that site is really different. And I think even kind of if we look at other industries that have successfully deployed robotics, they have deployed robotics in comparatively structured environments, right? Like, for example, industrial arms or other industrial robots used to be caged away from people, so they were in like a pretty controlled space. Even autonomous cars, yes, that's a very difficult autonomy challenge, don't get me wrong, but when you're on the roads, there are certain rules of the road, right? In terms of like, don't drive when there's a red light. And then to the most part, you have lane markings. Similarly for drones, right? There are airspace integration rules, there are rules on takeoff and landing procedures. And what a lot of these rules, they kind of put some structure to a rather open space. But for a lot of our deployments, right, even when we have the autonomy stack ready, the safety stack ready, and we go to a new site, there are times when we'll walk into a warehouse where the floor is completely empty one day, but the next day you have a bunch of different boxes and carts, and a week later the layout looks completely different. And so even within this like collection of warehouses and industrial settings, the deployment side is very dynamic, very unpredictable. Hospitals also on the other side, very different depending on the type of hospital you're in, if it's just a medical clinic or an actual hospital. And again, the way people move around proxy is very, very not consistent, right? And so what we really see is actually, safety also relies a lot on autonomy to just come up with a good approach on how are we going to navigate this space. And then use that as a starting point to then design a good system and then layer on a safety approach on top of that that actually helps autonomy as well.
Is there standards you can follow in these different industries? Or?
Yeah, that's a great question. Actually, I mean, robotics is not an industry, right? Like you have robots that are deployed in different industries, and you'll see that the standards landscape is very industry driven, right? Cars have their own standards, airplanes, drones have their own standards. And even in the indoor robotics space, what we see is there are, again, application or use case specific standards, right? So there's an AMR guidance for industrial robots. There's another guidance for AMRs or autonomous mobile robots in a hospital setting. And they're very application driven, or kind of how do you deploy a good autonomous robot in these settings. And then what you have is a more foundational layer of functional safety standards. And those are essentially that regardless of where you're putting a robot, let's say you want the robot to meet a reliability target, here's how you build a good fault tolerant system. And so I think it's a combination of a lot of these different standards that give you a lot of different perspectives on safety so that you're able to do both the really functionally safe fault-tolerant system design, and then also balance that with like trustworthiness features that are ensuring that your deployment is also safe.
And do you think that makes your job kind of, if you have to follow a particular hospital safety standard, does that make your life easier, or is it just more paperwork to do?
I mean, I love safety, and I'm also a roboticist at heart. And also I think a lot of safety engineers are also, they just love engineering. And so I see it actually as a fun problem. I don't know if it's easy or hard, but it's definitely fun in the sense that I think this really, varied standard landscape actually creates a room for both safety and autonomy engineers to be creative in the way that they want to approach this problem. It's rather than just giving like one path and here's how you build a safe system and that's it. Actually, no, we have a lot of say in how do you want to approach safety in collaboration with autonomy.
Awesome. So you've created a system, you have some understanding of its performance, you have some creative approaches in safety. I'm sure Cobot has some very tightly kept secrets on how to do that. You've deployed the system in the field. What's the most important or valuable operational data you can get back for actually understanding if your system is performing? This is a question for you both.
Mm-hmm. Yeah, I think, we've talked a lot about data at this conference, and data is really critical for both autonomy and safety. And in the end, both use the same data. So, it's the data, and that's one advantage of robots, is robots naturally collect data. So there's obviously the robot logs of what's going on within the software stack and any faults that might have happened. And then there's the sensor data. So you have a data-rich environment, which is great for both aspects. From the autonomy side, when we look at field data, we're really looking at a few different things. So one is, I'm not talking about the data for training, but more the data of like, how are you assessing the performance of your robot? So one side is looking at, hey, the robot got stuck somewhere, or the robot didn't complete its task, or the robot was going too slowly. What's going wrong with it? And so that's diving into the logs, sometimes the sensor data, really trying to understand, hey, what went wrong, so that you can go and fix it. And then there's the other side of, okay, we did some fix, or we just added this great new feature, or we're deploying a new model, and how is it really performing in the field? And so you want to say, hey, were there any unexpected things that happened, which probably everyone who's worked in robotics knows that the unexpected is going to happen.
Who's ever had a robot kind of drive off into the sunset out of control, right? Like several times probably? Hopefully under safe testing environments?
Yeah. So from an autonomy perspective, we're really looking at that. Like, how is our autonomy stack performing? How do we make it better? And data to like either validate or show that, hey, what we just did had something that we didn't expect.
Awesome. And can you reuse the same data sets that Heidi's collecting?
Yeah, so I think the base data is like to Heidi's point, right? We're getting so much rich information from just the robots running around that it helps safety also. And I think from a safety standpoint, we're basing our story on the same data, but it's like a slightly different story that I am interested in as a safety engineer. And what that means is at any given time, what I care from a safety perspective is what is happening inside the robot and what is happening around the robot. So kind of to Heidi's point, right? Like when you look at our logs and you see a robot is stuck, that's definitely an operational concern, but then from a safety standpoint, I want to know why it was stuck. Were there some faults within the system? Did we have like a compute stack reboot, or did we have some latency? And if we had latency, we can go through the logs and see what caused that. And then we can also then paint a safety story, which is, well, the bot came to a stop, meaning systematically it responded to that situation in a safe way, right? And then holistically, we can together look at that same data from these two different perspectives, and then that just paints that reliability case, which is reliability is gonna help both safety and autonomy, because you want the robot running all the time, and I don't want the robot stopping all the time, right? Because a good safety story isn't just like, oh, nothing happened, but is that you can see something happen and that the robot and the system actually responded correctly, and the data helps you do that. And then the second point is, I think, and this is actually a pretty big challenge, I think, for robotics, especially in indoor environments, as we see robots scale in a lot of different spaces, is we need good ways of quantifying or characterizing the environment in which these robots are now going in. And so we use a lot of the sensing logs that we get from our bot to really characterize the space that this particular robot is deployed in. That includes things like characterizing what types of dynamic obstacles that we see, what were the range of obstacles that we saw around proxy, and what that helps from a safety standpoint is when we do our risk assessment, and a lot of you will hear a safety engineer on your team always bring up risk assessment. And the reason risk assessment is one of those things that safety engineers talk about all the time is usually risk assessments are really qualitative. But as you pull these data into your risk assessment process and quantify it, it actually builds the confidence in a lot of the safety choices and even performance metrics that you end up defining. So the more data you get to paint a safety story, the better.
Yeah, because again, if your robot's constantly stopping, it's very safe, but nobody's going to want to use it.
Yeah.
It makes a ton of sense. Heidi, a question for you. So where do you use machine learning or other similar approaches in your system? Where is it an appropriate way to deploy and to bound it in a way that it doesn't affect autonomy, doesn't affect safety as much?
Yeah, I think that's an interesting question in the sense that, like, clearly the ML, the trained models, are hugely accelerating robotics. So of course we're going to use them for all the core autonomy. Then the question is, can we also use them for, say, a safety critical software function? And some people have said, well, no, you can't, because the whole idea of a safety critical function is it's a simple monitor. It has a predictive, you input something, you predict the output, and then you can formally either prove that or formally test that every input gives the correct output. You're never going to get that with a learned algorithm. That's by definition. You can't say, if I give this input, I know deterministically I'm always going to get this output. And in fact, you always want to be improving the model. However, if you think about what the ML does and what we're trying to do with our robots is it's trying to solve the problem of, I'm putting this robot in an environment that's going to have something in it that I didn't expect. So something's going to happen. I modeled all the ways that people could walk in front of the robot, and I forgot to think about the person that could jump off the table in front of the robot. And that's just going to happen. They'll have that edge case. And ML algorithms have the capability to say, well, I didn't train exactly on that, but I can still do something that handles that edge case. So I think that's, for that reason alone, they're very promising to be putting into as part of our safety story to say, hey, we're going to use some ML that will be part of our safety stack. And then the way I think you can do that is you work with your safety engineers on the risk assessment, and you say, okay, here's the way that I'm going to handle my ML trained software safety function is I'm going to have training data, I'm going to have testing data, and then I'll be able to test it to some level. And you're probably not going to get the testing data to say, okay, I'm going to get multiple nines of reliability out of this. And that's okay, because you design your system such that you say, okay, well, I'm going to say this is 95%, or I'm going to, we're going to really test it well, and we're going to get it to 97%. And then you either make that part of a redundant system, or you add some other layers of safety on top of it so that you can use that as part of your safety story, but it's not going to answer the whole safety story.
Yeah, that makes sense. And kind of the same question, but reverse for you, Ankita. Like, how does the safety system integrate with the autonomy stack?
Yeah, that's a good question. And I know we have a lot of people from a lot of different industries in the audience. So let me start with answering that question with first grounding on, if you look at a lot of the robotics space today, there's a very common architecture and that's why we kind of separate autonomy stack and the safety stack, because the premise of functional safety, you're building like a really reliably safe system, is that you have the autonomy stack, which is doing the bulk of the decision making. It's doing the perception, the path planning, any other reasoning, and also the motion planning, actuation part of it. And then you have a separate safety system that is basically monitoring what autonomy is doing across a lot of these different tasks. And if the system were to go out of bounds, it intervenes, right? A good example, or a very simple example, is, let's say your bot has an acceleration limit, right? Like, you have an acceleration limit because you don't want your machine to tip over. And if the safety system monitors the acceleration limits that cross a given threshold, it'll intervene and likely get the bot to a stop. Again, just bringing the bot to a stop, probably not like the ideal solution, because the ideal solution may be that you want to cap off your acceleration, right? And so what that means is you're putting a constraint on your controller, and now by putting a constraint on your controller, you're actually bringing the task of autonomy that was doing motion planning to a certain degree within your safety envelope, right? And so I think the reason I bring that example up is I think as an industry, as users around robots, we're going to start demanding these robots to not only be safe, but also be intelligent. Meaning just having a safe response is not enough. You want a safe and intelligent response, which is going to start bringing portions of autonomy into your safety envelope. And then kind of going back to the ML point, I think that's going to help us deploy some ML-based safety functions, because now you have a portion of autonomy and safety together, kind of sharing the burden of safety reliability.
Yeah, I've seen recently there's been some work in AI safety standards.
Yeah.
And that must be pretty exciting in your world to follow along that development.
Yeah, 100%. And I think actually I'm a huge fan of the autonomous vehicle field, and I think the automotive field has done a really great job in kind of showing how are ways in which you can actually balance autonomy and safety and introduce machine learning models in a lot of different capacities into your safety stack. So yeah, I think there's a lot of exciting stuff that's going to be happening in robotics soon.
Absolutely, absolutely. So excitement, we're moving forward. I think the traditional image, I had before and I'm trying to fix is that you have engineering and autonomy trying to push the company forward, and then you have the safety team saying, that's too dangerous, you got to slow down. How do you make sure that doesn't happen, Heidi? How do you actually make sure, like, does it slow you down? Does it streamline it? Does it change your thinking? How do you integrate, and how do you actually co-pilot this effort?
Yeah, I do think you really want to work together, because in the end you're solving the same problem, right? Because of course the safest airplane is one that never leaves the ground, and nobody wants that. So you have to start from we are working towards the same goal, and from there, from a software side, I think there can be this idea of like, oh, safety's trying to put limits around me. And I think if you reverse that and you say, okay, actually what safety is doing is saying, let's build a robot that's really reliable. And so especially from the software side, you think about, oh, wait, if I have a robot that's really reliable, that sounds like it's actually going to be an accelerator to me, not a decelerator. So, as an example, if you look at, from the safety point of view, saying, oh, I want to ensure that all the hardware that we put on the robot is going to do the same thing every time and not be flaky and not sort of do something odd or not quite turn on but silently fail. So really bad from a safety point of view, also really bad from an autonomy point of view. If you have a piece of hardware that you're trying to test, something's going wrong, and what it is one of your connections to a sensor was bad, and you thought it was your software stack, and you just spent days trying to debug it, and no, it was a fault in your wiring. So as you design your system, both from the hardware side and from the software integration side, to be very reliable, that can then speed up your autonomy development, because you've now got a very solid base, and you can say, oh, the robot is not moving the way I want it to, that's my motion algorithm. That's not the motor is just acting up funny. So that part has kind of the same goals. And then the second part that I think can be really helpful is if you have that safety function in there and you have the bound of the confidence that you know the robot is going to be safe, then you can start pushing the boundary more on the autonomy side in test. And you can say, okay, we're going to test these things, in our lab, and we're going to try some different things that maybe push it a bit. And we know it's not going to hurt anything because we've got the solid robot. We've got the framework there, and we know that we can work within that to improve the performance.
You can push right at the edge of performance.
Right. So you can push right to the edge. Yes.
Yeah, I mean, to your earlier point, that I guess the summary is you're telling me I get to blame the electrical team less when something works properly, and less finger pointing of your motor's not working properly.
Yeah. And I think one of the things in the past that where I have had friction with the safety team is some of the constraints of what are the constraints on the robot, and oh no, you can't go that close, and those are things that if you approach them correctly as this is an engineering problem we're going to solve together, because we do need to get through a narrow pathway. So how do we do that, and how do we do it in a performant way, in a safe way? And then once you've shifted your mindset from oh no, I want to do this from an autonomy perspective, but the safety engineer is saying I can't get that close, to we both want the robot to do this, so let's figure out how we do it safely and in a high performance way.
Yeah, and I think especially earlier in the process, right? That's a discussion to have day one, not the day before you ship.
Earlier, and that's I think a key lesson is that you do want to have the autonomy and the safety discussion early.
Yeah.
And not leave either one of them later.
Yeah, everybody loves the engineering meeting the week before you ship of we've got to change priorities here.
Right.
Yeah.
Everything you've done so far is no good.
Yeah.
So closing question then for you both. What does it mean? How do you know it's actually safe enough to scale?
Yeah, so I think, there's some idea we'll scale when we're fully safe, that statement is meaningless.
100% safety.
So really, it's, the 100% safe. When people say, we want this robot to be 100% safe, I think, that doesn't mean anything. So what you really want to do is think about, as Ankita was saying earlier, what is the environment we're going to be in? What is, considering the scale that we're planning to get to, what is the level of risk that we can accept, given the benefit that this robot is going to provide? And then you design your system to that level. You say, okay, now we've designed our system that we think its safety meets this level of risk that we're designing to. And then you're ready to scale to that.
Yeah.
In your view?
I mean, I agree with that, right? But I think there's also this point that even once you've proven to whatever your safety level is and you've built your system to that, the reality is that safety is not this one thing that you achieve in one point in time and then you're good to go. You have to maintain your system at that safe state for a while, right? So, and that's why you take your car into servicing once or twice a year. That's also the reason why you're standing at your gate and you see your aircraft outside, but your flight is canceled, is because they failed a maintenance check or they did something that is now kind of compromising the safe state of the machine, right? So I think, I think the closing answer is you have to do the work to determine your risk level to prove that you've kind of met that. And then also make sure that it remains valid for as long as your machine is operating.
So I can't de-staff the entire safety team as soon as we ship. All right, well, thank you very much both.
Yeah, thank you.
Thank you, Ilia.